So in the last exercise, we created the bet format, and I just want to go a little bit into detail about this bet format because it's quite useful. It's a very simple format. And as you can see, or as you just saw, we can load bet formats into IGV. And that just helps us whenever we look at things in a genome browser to quickly create our own little files that we can load as a little help. So this bet format is the abbreviation for browser extensible data. And this is, again, a tab-separated format, so you can load it in Excel if you want. And again, it has just a bunch of columns. And the first 3 columns are the most important thing. As soon as we have the first 3 columns, you can load it in IGV already. So column 1, again, is the chromosome. So that needs to match exactly the identifiers in the FASTA file of the reference. And then you have a start and an end. And in brackets here, we have this 0-based. And that is a different to the GFF format, which is 1-based. What does it mean? If we have these positions displayed, in a GFF, we would count the first nucleotide in the reference with 1. Here in the bet format, we count the first nucleotide in the reference with 0. It's not ideal that this is different, but that's just how it is, and we need to live with that. So first 3 columns are mandatory, and then whatever comes next is optional. Importantly, if you want to use any data of one of the subsequent columns, you do need to have entries in the previous columns. So if we want to use this item RGB, for example, we need to have entries for name, score, strand, thick start, thick end. Okay. So let's have a little bit of a look into what we just created. I'm going back to the VM. And I had created this SR33 versus 1d.blastn.tsv. We create from that, we converted that into a bet file. And what I've tried already in the break, and I need to do that again, is just copy this file to have a little bit of a bet file that we can play around. So just pretend this test.bed wasn't there. What we want to do is we obviously want to create that now. So we copy our sr33.tsv.bd into something called test.bed. So now let's have a quick look into test.bed. So these are our entries. It's pretty much similar to the BLAST output, but we needed to change that a bit because in the BLAST output, in the tabular thing, in the reverse complement hits, you would always have the second hit first. Whereas in the bet file, even if it's on the reverse strand, you have the smaller position as the start position and the bigger position as the stop position. And if it is on the reverse strand, you would just change this column to a minus rather than having it at a plus. As you can see, we have, again, a comment line here that starts with a hash. And we have our chromosome, we have our start, and have our end. So first 3 columns I said are mandatory. And then what else do we have? We have a name. We have score, strand, name, score, strand. I think that's what we have here. We have a name, which goes from here to here. And then we have a score. This seems to be 0 all the time. So there's no entry for score, just something default. And then we have a strand, which is always plus. That means all our alignments have been on the... Now, let's assume we want to play around a little bit. We already loaded this into IGV, and we obviously can have a good look at that. But let's try to use this item RGB, because I quite like that. So item RGB allows us to have some of these entries in a different color code. So everything in IGV was blue, unless we start messing around a little bit with that. So very quickly, what I'm trying to do is I take this test.bed and I open that with Excel or something close to that. Take this LibreOffice again. Let's have a look. This is tab separated, and I think, oh yeah, we need to start in row 2 because the first thing is a column. Let's load that. And remember, I said if you want to have one of the subsequent columns, you need to use you need to have entries on all of the others. So the other entries right in front of us are thick start and thick end. This is if you want to display any UTRs or something, but in this case, we just start from the beginning. We copy and paste our normal start and end position as thick start and thick end. And then here, in this column, this is now our item RGB column. Here we can enter RGB values. So this is RGB for red, green, blue. And if we have something on 255, this would be in that channel the full color, where it is, if it's 0, it's none at all. So we take it very easily. RGB, if we have R on 255, and then comma G, green on 0 and blue on 0, that should be a red entry then. And we can do the same game somewhere else. So let's say we have all of these first ones, we just have them in red. And then maybe here, some of these we have in green, 0, 255, 0. Some in 0, some in green then, and then let's have some blue entries as well. 0, 0, 255. And paste that. So let's save this. I think now we have to battle a bit with this LibreOffice because it doesn't allow us to save this as a bat file, or does it? Let's see what happened here. Did it create something else? No. Okay, so now we have these additional entries here in our test file. So if I now start IGV again, should still have our chromosome 1D loaded from the last time. We can load this test.bed. By the way, we can obviously load multiple tracks. So I'm just for fun loading this one as well. If I have Control pressed while I select several ones, I can load several at the same time. So here was our entry. Now you can already see that we have introduced a color coding. We have some of the hits in red, some of the hits in green, and some of the hits in blue. Okay, so this is just bat format, but also once we have a bat format, it's very easy to just load it in a text editor or in Excel or something and manipulate it and just add a couple of additions. Don't worry too much, just make a copy of it. And if you make any mistakes, the worst thing that happens is that your new file will not be displayed. And then you need to mess around a bit until you are able to get something out of that. So what we do now is we start with the next exercise, and this is actually going into our overall program again. So the idea is, I should have changed that, messed it up. I didn't. We need to stop here. I just go back to that, and then after I've talked a bit, I make a break, go to the exercise. Okay. So now, so that was the bed format. We go to another exercise, and now we go into this overall project where we try to look at the resistance gene that is hidden in the Cariha genome. So just imagine in our project, we have done genetic mapping, and we have identified 2 markers that are flanking our interval, where we now want to do a candidate gene approach and where we now want to explore a bit more. And all these explorations we can support with IGV. Now we know how to load sequences into IGV and how we make things visible, just converting that into bed files. And we'll see another, a couple of other formats that we can load into IGV. So this is just going back into BLAST. There will be a file called markers.faster. This is the underlying sequence the markers have been created from. So you need to take those. You blast them against the Cariha genome, and then convert whatever comes out again into a bed format and load that into IGV. If you want to work with the entire genome, you can do that. It will probably not work in the virtual machine. If we're in the virtual machine, we will use the sequence locus.faster as our reference. So I just show where these data are, and then first we need to quit this IGV. So at the moment we're in the home directory. Let's look into data. In references. So in these references, we have a file called locus.faster. And we also have a file cariha v1.locus.gff. So this locus.faster is a little part of the genome. And this is the part we're going to interrogate a little bit more. So all the data that we are using subsequently is a subset of all the main data. And this basically is made for running fairly quickly for this exercise, and also to work in our virtual machine. If you have extensive computational resources, please feel free to download the original data and use that with the original genome for all your mappings and your blasting. So for now, we use this locus. Again, you need to make a blastable database, and you need to use your markers.faster, which is here. This is the content of your 2 markers. Let's have a look in there. Less data. So we have marker 1, which has a sequence, and marker 2, and that's the end of it. This is basically a multiple FASTA file. So in here you can see this is going to be our query sequence. So you can play with this. This is the first time that we are having multiple entries in our query file. You can see what happens then. The task is again to create a BLAST output and to convert that into BED, and then to visualize that with IGV. You need to keep in mind that now our reference is the locus.faster, and also our blastable database has to be locus.faster. And I just give you a few minutes to try that yourself. So please pause this video and give it a go. And then we can try to do that together. So I hope you had a little bit of success. Let's give it a go together. Again, we do not want to work in our data folder. So I go back to my exercise folder and I copy the data over. Maybe at this point, I'm not interested in any of the data that I've been using before. This is all intermediate data, so not important. I just remove all of them. Okay. So then we want to start with the locus.faster. And we copy that into our folder, and then we copy also the markers file into our folder. No, missing destination. We need to copy to dot or dot slash. Okay, we have the two files. Again, running blast. First create the blastable database. Make blastdb minus in minus db type nucleotides. Okay, and then we create our, we run our blast n minus query, and then the query was markers. Keep in mind, I hope you remember that from the Linux or the command line shell session, you have the tab autocomplete that helps you to finish these things very quickly. So you just have to hit the tab key on your keyboard, and then you have this autocomplete. Same is true for the locus. And then we want an output format 6 for tabular, and we need to define an output file, markers versus locus dot blastn dot tsv. It's a very long name, but that helps us not to forget what it actually is. So if we look at this data in half a year, we still might be able to figure out what we actually did here. So I've got that file, and now I need to convert that into BET format. That was blast to BET for markers versus locus. Okay, quickly see that we have some content in there. We have created this BET file just to show some other commands. Again, cat, which is concatenate and then display on screen. Markers versus locus.tsv.bet. So we have good entries in here. So that means we can try to load that now into IGV. Now, importantly, it says it can't locate our previous genome because I just had deleted that. Otherwise, we would have to remember really to load this locus, because of course, this locus might have different sequence identifiers. It also has different positions. So always whatever is in the first column of a GFF file or a BET file needs to match exactly the sequence identifiers, what we have loaded. So here we now need to load our locus. And then once we've done that, we can also load our markers BET file. And you can see we have several hits here, which is slightly annoying, but of course, we will have the best hits. So this hit has a length of 830 bases. What is the other one? This looks a bit shorter. What is that? Yeah, this is just 600 bases. But what we could do now, we've just learned that we could go into the blast output, see what are the best hits for marker 1 and marker 2, and color them green, for example. So this one is very short, this one is very long. So coloring it green, oh, this is more interesting. We actually have several hits here. So it probably makes sense to just get rid of all of that, because at the end of the day, when we work with our data, we want really just these two entries, marker 1 and marker 2, where they match, that we know exactly between this and this, we need to look at all our genes, and we don't want to be distracted by these other entries. So the two ways to do that is, well, coloring and make all of these red, or simply going into the bed file and removing these other lines. So if we try to do that, need to get out of IGV first. And then we need to look at, for marker 1, let's have a quick look in our TSV file. Less markers versus locus to TSV. For marker 1, we have two entries here. This one is the best one. So this is hit start and hit end. If we keep in mind 43, the entry that starts at 43 KB is the interesting one, and this other one is not important. So now I could go into the bed file, and so we were interested in marker 1. We had one entry here, and we have one entry here at 43. This was the one we are interested in, and this was not relevant. So we could simply delete this line. Whoops, deleted a little bit too much. Okay, we write out, and we get out of this. So now if we go into IGV again, can load our bed file. You can see that the other entry for marker 1 is gone. And we could do the same game for these other entries that are not important. But I leave it to you to do that.